In this work, we present a self-contained, multi-rotor platform with autonomous obstacle avoidance software as a means to aid in the teleoperation of the platform by a human operator. The platform, in addition to standard structural components, consists of a set of sensors for state estimation, sensing the environment, and to provide visual feedback to the operator. A small single-board computer makes the platform independent of external computational units. On the other side of this setup is an operator's desk which is equipped with a computer monitor and haptic control device to provide visual and haptic feedback to the operator. The main software components, which we detail in our work, consist of a dual Kalman filter state estimator with on and offline bias estimation, as well as our obstacle avoidance algorithm. We have performed thorough experimental validation of our platform in different optical setups, which we will see examples of now. The experiment shown here is a zigzag flight between four walls. The visualization on the top right shows the obstacle state. It is created using a bin occupancy filter in a local cylindrical frame with fixed size, using measurements from the depth sensor, and updated based on an estimate of the robot's motion. This is a probabilistic representation where red points represent cells currently in the field of view of the sensor, and green cells represent previously visible cells whose position is now being estimated. As the operator commands the robot to go forward, the algorithm extrapolates the robot's trajectory and alters the commanded velocity in order to avoid collisions. The results of the state estimation and the behavior of the avoidance algorithm are shown in the graph on the bottom right. This video presents the avoidance capabilities of our platform with horizontal obstacles. The onboard camera view shows how the robot is commanded, similarly as in the previous experiment, to fly directly towards the edges of the obstacles while the algorithm finds new, optimal directions that minimize the change of the user input. The velocity commanded by the operator is represented by the blue arrow attached to the gray cross representing the UAV in the 3D visualization. The output of the algorithm, which is the actual reference velocity, is represented by the red arrow. The operator is constantly aware of the algorithm's actions through haptic feedback on the input device. Additionally, the obstacle avoidance is mainly passive, which means that when there is no input from the user, the algorithm will not perform additional motions and will only actively compensate in the case of drift.